Alright, this is my first shot at filming a video for Algebra 2 content. Today we're going to begin exploring polynomial and rational inequalities. Our first objective is that we can solve polynomial inequalities algebraically and graphically. As a type of warm-up, I'd like you to pause the video and solve the quadratic inequality x squared plus 4x minus 21 is less than 0. Go ahead and give that a shot. Alright, I hope everybody had a chance to try and solve this inequality. Chances are, when you saw the quadratic, that your first reaction was to factor it. And that's a good first move. So we know that our quadratic expression is equal to the quantity x plus 7 times the quantity x minus 3. And we need this to be less than 0. Now, after factoring, many of you probably decided to take each factor and to state that each factor could then be less than 0 and solve those linear inequalities to give us x is less than negative 7 or x is less than 3. Let's take a minute and check a solution in this set. When we've said x is less than negative 7, we could check a value x equals negative 10. That should make this inequality true if values less than negative 7 are in the solution set. By substituting negative 10 into our original polynomial and simplifying, we end up stating that 39 is less than 0. Obviously that is not true. So where did we go wrong? If we go all the way back up to our work where we factored the inequality and then stated that each factor is less than 0, we've made a common error here. What we've done is it appears that we have used the zero product property. Remember that the zero product property states that if the product of factors is equal to 0, then at least one of the factors must be 0. However, we don't have an equation here. We have not stated that the quadratic is equal to 0. And so we cannot use the zero product property, and all of this work fails. Another way to see this is to graph the inequality. So let's graph f of x equals x squared plus 4x minus 21. The same inequality, or the same quadratic that we were working with initially. To graph a quadratic in standard form, I need to find the axis of symmetry. We should be comfortable with that work by now. X equals negative b over 2a leads us to an axis of symmetry at x equals negative 2. Once we have the axis of symmetry, we can substitute that value into the polynomial and find the vertex. So that work gives us a vertex of negative 2 comma negative 25. If I know the axis of symmetry and the vertex, finding the x-intercepts can locate more points on our parabola. We've already done the work to find those x-intercepts. We talked earlier about the zero product property. Now I can employ it because to find x-intercepts, I need my quadratic expression to equal 0. That equality is important. So using the zero product property, I end up with x-intercepts at negative 7 comma 0 and 3 comma 0. So putting all those together on my graph gives me a graph that looks like this. Here's our vertex that we found at negative 2, negative 25, and our two x-intercepts. So remember, the reason we started to explore this graph is we want to solve for the function being less than 0. Our function was the quadratic expression x squared plus 4x minus 21. So what does it mean for a function to be less than 0? For a function to be less than 0, it means all the outputs to the function lie beneath the origin on our graph. So if I look at my graph in here, where I've colored green, every single one of those ordered pairs has an f of x value that is less than 0. Therefore, we know that the solution to this inequality is that any x value between -7 and 3 satisfies our inequality f of x is less than 0. Again, look at the green color on the graph to see how those x values correspond to f of x being less than 0. If you're not using inequality notation for solution sets, you may choose to use interval notation to write the same set of numbers. These two solutions are equivalent. We know that our given quadratic is less than 0 if x is between -7 and +3. Let's take a look at another example. As we start our example, I'll remind you that when we look at our graph, f of x will be greater than 0 for any ordered pairs located in quadrants 1 and 2, in other words, above the x-axis or above the origin. F of x is less than 0 for any points that are below the origin. Using that knowledge, let's solve this polynomial inequality. The quantity x plus 3 times the quantity x minus 1 squared is greater than 0 by graphing this function. In order to graph the function, things to consider from prior knowledge: end behavior. We can see that the leading coefficient of this function is positive, so as x approaches infinity, f of x must also approach infinity. And the polynomial is cubic, and since it's of odd degree, as x approaches negative infinity, f of x will also approach negative infinity. Other important things to see from our polynomial function are the x-intercepts and the y-intercept. The x-intercepts can be found just by looking at the factors above. We know that if x plus 3 is a factor of the polynomial, then the ordered pair -3, 0 has to be an x-intercept. Because the factor had a degree of 1, this x-intercept will be a spot where the graph crosses the x-axis. Looking at the factor x minus 1, quantity squared, gives us an x-intercept of 1, 0. We also know that the graph will touch the x-axis at this point without crossing it, because the exponent of 2 on the factor is even. To find the y-intercept of this function, I can substitute a 0 for my x values in each factor and simplify to get a y-intercept of 0, 3. Take a moment, pause the video, and use this information to graph this function. So your graph should look something like this. You can see the x and y intercepts and the end behavior that we referenced above. Now, look at the original inequality, which said the polynomial was greater than 0, and consider why I have colored part of my graph green. At each of the points that I colored green, f of x is greater than 0. So this allows me to find the solutions to the given inequality. In this case, my solution set are all of the values from -3 to 1, or from 1 to infinity. Ask yourself for a moment, why did I exclude 1 from my solution set? If we look back at our graph, we can see that if x is 1, f of x is equal to 0. And a number that is equal to 0 cannot be greater than 0. And that is why 1 is not included in our solution set. That's how we solve polynomial inequalities graphically. The next thing we're going to do to satisfy our objective is we're going to look at solving polynomial inequalities algebraically. To do that, we're going to rely on a definition for a term called the critical values of a polynomial. And the critical values of a polynomial are simply the real zeros of that polynomial. So let's take a moment and look at how we can use the real zeros of a polynomial to solve polynomial inequalities. examined this quadratic inequality as part of our warm-up. We tried to solve it algebraically using the zero product property and saw that that failed. Now we're going to look at solving it using critical values. So our definition of critical values was that the critical values are the real zeros of a polynomial. If I set my polynomial equal to 0, now I can use the zero product property. And so without repeating work that we've shown before, I'm just going to skip straight down to those two values, x equals -7 and x equals 3. And those are known as the critical values of this polynomial. After knowing that these are the critical values, consider what we saw when we graphed this function. We know that the graph of any polynomial is both smooth and continuous. And therefore, the only points that can have f of x be positive to one side of the point and negative to the other side of a point will be the x-intercepts. And the x-intercepts on a polynomial are found at the critical values. So what I'm going to do is this. I'm going to examine a number line. My number line is the real number line containing all real numbers from -infinity to positive infinity. And I have graphed my two critical values, -7 and +3 on the number line. You'll notice at each of those points that I have drawn an open point on the number line. -7 and +3 are not solutions to my original strict inequality because my inequality stated that we must be less than 0, and these two values lead to f of x being equal to 0. After graphing those on a number line, I'm going to identify the intervals within the real numbers that I have created. I've created one interval from -infinity to -7, one from -7 to +3, and a third from 3 to infinity. Within each interval, I can explore a value and see with the corresponding f of x value. Let me show you what I mean. So, for my first interval, I'm going to test the x value -10. Now, -10 is between -infinity and -7. When I substitute -10 into my original polynomial, as we did earlier to check, we ended up with a value of 39. 39 is positive, and therefore that value is not a solution to our inequality. Because -10 is not a solution to the inequality, no values in this interval will be solutions. Now let's explore our next interval. Our next interval is from -7 to +3. An easy test value between -7 and +3 is 0. And when I substitute 0 into my original polynomial, the output is -21. -21 is obviously a negative number, and therefore is a solution to our inequality, which said that the polynomial had to be less than 0. Because 0 is a solution, every x value in this interval is also a solution. Again, if you connect that to your knowledge of a graph, the polynomial graph must be smooth and continuous, and that continuity means that we cannot have an f of x that is positive in this same interval. For my third interval, from 3 to infinity, I'm going to test the x value 10. Substituting 10 into my original polynomial will give me a positive output. That positive output cannot be a solution to the original inequality, and therefore no values in this interval can be solutions. When we look at our original inequality that we started today's exploration with, we again see that the only solution is numbers on the interval from -7 to +3. We have now shown this graphically, and we have verified it algebraically. This table that you see with the critical values on the number line, the intervals, the test values, and the conclusions reached are what you will use to justify the solutions to a polynomial inequality when you solve algebraically. We're going to look at one more example together, and then we'll give you some to practice on your own. The last example we're going to look at together is we are going to solve the inequality x to the fourth is greater than x. Now, because we're relying on positive and negative in our conversation, we don't want to compare x to the fourth to x. Instead, we want to subtract x from both sides of the inequality and compare x to the fourth minus x to 0. In this case, we have the strict inequality that our polynomial is greater than 0. I can factor this inequality by using the distributive property to factor out the greatest common factor x, and then to factor the difference of two cubes into a binomial and a trinomial. I know that the product of these factors has to be greater than 0. However, I also know that I cannot use the zero product property to solve an inequality. Instead, I need to rely on critical values. Pause the video for a moment and use the definition of critical values above to solve for the critical values of this polynomial. All right. To solve for the critical values of the polynomial, I am going to set my polynomial equal to 0. That's the change from here to here, and the reason it happens is because I am now searching for critical values. At this point in time, I can use the zero product property to solve for my critical values. My first factor is x, so the critical value is x equals 0. My second factor was the binomial x minus 1. When I set that equal to 0, I solved for the critical value x equals 1. And my third critical value was the quadratic factor, my third factor was this quadratic factor, x squared plus x plus 1. And when I attempt to set that equal to 0 and solve it, I used completing the square here, I end up at a point where I'm going to need to square root a negative number. We know that the square root of a negative is imaginary, and therefore this quadratic has no real solutions. We said that the definition of the critical values of a polynomial function were the real zeros of a polynomial, and therefore this quadratic contributes no critical values. Our two critical values will be 0 and 1. As in the previous example, we have a strict inequality here. We have said that we strictly want to be greater than 0. Therefore, the critical values 0 and 1 are not solutions to my inequality, and I've graphed them on my number line with open points. At this point, identify the three intervals created on our number line, negative infinity to 0, 0 to 1, and 1 to infinity. After you've identified these intervals, you can simply test one value within each interval to see if the interval gives you a solution or not. Go ahead and pause the video, and you test a value within each of these three intervals. All right, we're going to take a look at my test and realize that I may have chosen different numbers than you, but I first chose the number negative 1 to test between negative infinity and 0. Substituting negative 1 into my original polynomial inequality gives me a positive output, and therefore this interval gives me a solution to the inequality. Here are my test values for the other two intervals. I've tested 1/2 as a test value between 0 and 1. That corresponded to the polynomial function having a negative output. And then I tested 2 for a test value between 1 and infinity, and this corresponded to my polynomial having a positive output. Because my original inequality that I was solving said that the polynomial would be greater than 0, each of these two positive intervals contributes to my solution set, and my solution is negative infinity to 0, union 1 to infinity. I hope that the examples we've looked at here have helped you to understand how you can solve polynomial inequalities, both graphically and algebraically. Now it's your turn to do some practice. Thanks for watching.